Good morning, everyone. What I'm going to do today, probably sharing our near 10 years running models in a very heavily regulated industry. Many of you that's not familiar, banks in the US, we have to comply with a certain kind of expectation that regulator have. So many of you that's in financial industry, so particularly with US banks, in the post the crisis in 2008, Federal Reserve and OCC, our financial regulator, issue what they call it model risk management guidance. So those are things that we have been practicing the last 10 years, and something that maturing, and all big banks in the US practice that. And then when AI and machine learning getting very, very rapid adoption, of course, we apply it accordingly as well. So these are the things that I'm going to share. I'm going to share with you some of the things that we, in our mind, what we worry about, what our regulator worry about, and the direction and the approach that we do, particularly for high-risk application. A lot of example I'm going to do today, but I probably will be at the a bit high level presentation. Of course, we can do, if interested, we can talk about a lot of technical side as well. Okay, let me start with a bank runs by model. We run model for everything we do. From something very, very mundane of listening customer call and detecting whether this call is fraudulent or not, or if customer complain, where the complaint should be routed to. So very, very mundane like that, all the way to whether banks will survive in the next recession, which probably will happen anytime soon or very near down the road. So with that, give an example on the some of you that's not very familiar with the banking industry. In the stress testing, what we call it annual stress testing. Stress testing is like the World Cup of modeling. That's where we run for a company like Wells Fargo, about 600 models that we run, thousands of people involved, very intense 3 months period where everybody running, getting result, consolidate, and all of those things. So very, very massive exercise that we do all the time. And this is very, very important exercise because the result will be evaluated, will be judged by regulator. So we run model pervasively because our data is very, very rich, data rich, and all the decision data driven. Very, very process heavy. Bank is very process heavy, from loan application to loan approval, from disbursing fund, very, very process heavy. So when we apply model, typically we apply model in 2 areas. One is model for financial purpose, financial model. This is very, very well-established process for us. Model for credit approval, model for forecasting loss. It's model for managing market risk, model for managing liquidity risk. Those are very, very well established. In that area, typically because it's long established historical things that we have long history, long experience running this model, the technology infrastructure are available. So in terms of building model, developing model, deploying model is a lot easier. And the other aspect that's rapidly developing, rapid adoption are really more on the non-financial model. This is related with customer service, related with detection of financial crime, related with more online marketing, compliance, detection of conduct. For example, we serve our customer on the trading floor. Company want to trade, we facilitate the trade. We want to make sure that our trader have the best behavior. They are not taking advantage of customer. They are in the acting on the best interest of customer. So a lot of you heard a lot of scandal. Big banks have a lot of scandal about this when they get fined by the regulator. So we monitor every chat, every email, every communication that we do through our model too. So all kind of model that we do across the board. I think that's the beauty of in something like banking industry. We apply model. We have in many aspects of what we do. We have several thousand models in our inventory that we manage, we maintain, we monitor, etc. So in terms of scale of model, I think we are way up there in terms of scale deployment of model. But what we care about, because we use model, because a lot of critical decisions that we do are driven by model, including making decisions to people's livelihood. We are approving loan. When we are approving or declining loan, it's deciding future customer socioeconomic. It may not be their only socioeconomic, but their future generation. And when we apply model, we apply it to many people that impact the society. So a lot of socioeconomic gap can be damaged because of that kind of algorithm and decision. So we care a lot about model failure. We believe all models are wrong. Every model are wrong. And when they are wrong, they create harm. If it's credit model, create credit risk. Bank lose money. If it's market model, create market risk, bank lose money. But there's also other model that model can create unintended consequence too. Credit model can be discriminatory to age, to gender, to race. So all those things that we need to worry about. I give you an example on the lending. Let's say credit approval. Give an example in terms of credit approval, and this is the challenge that we have to do and we have to be in mind. Credit decision in the U.S. is very heavily regulated. We have law, Equal Credit Opportunity Act. The decision cannot be discriminatory. So to give an example, approving credit card, or someone apply credit card, are we going to approve the credit card or not? What variable we can and we cannot use is very critical from the get-go. For example, the size of mortgage. How big is your mortgage? You cannot use that. Very predictive thing to say, is this person going to default on credit card or not? Very predictive. But you cannot use it. Why? Because market size in the U.S. is racist. Based on the size of mortgage, we can infer what race the applicant is. So a lot of variables that correlated to female and male and all those demographic cannot be used. So language model is very problematic. Male and female in English language write differently. So we have to think about this. I give another example. Let's say your credit card, you do a transaction in your credit card. And transaction looks fraudulent, get detected fraudulent. And you have to verify your identification, for example. For some reason, you are being told you have to go to a branch. Seems very innocent, at most it's annoying that I have to go to a branch to unfreeze my account. For you and I, at most it's annoying. But think about for some people that have to work 2 or 3 jobs to feed their family. Going to a branch is about not feeding their family. And those people, those population came from certain demographic. So you have that problem. I talk about the natural language processing. We do a lot of natural language processing, listening our customer. do voice-to-text transcription, and then text go natural language processing, and then the complaint get routed appropriately to the right person, the right group who will process the complaint. So the model is very, very helpful. We can speed up the complaint resolution process. But for someone like me, who speak with very funky Indonesian accent, a lot of missing in the transcription process. The model that do transcription miss a lot of those. What happened? The model is discriminatory to specific people, nation, origin, or speaking language. So those kind of things that we worry about, not only the financial damage that we can have, but also we worry about the reputation damage. In our world, in regulated industry, and in the industry that rely on trust, people bank because they trust the bank. They trust with their money. So if our model is in trouble, discriminatory, something like that, it gets picked up by Wall Street Journal or get picked up by New York Times. Our CEO will be called by Congress, and the following month we will have new CEO. That's the type of thing that we worry about in terms of the damage that model can do. It's a very, very high-stake environment that we're dealing with. So with that, I share a little bit about the SR 11.7 OCC 11-12. This is the guidance, how people talk about responsible AI today, how to set up responsible AI, how to govern it. Banks, large bank in particular in the US, has practiced this for the last 10 years. It's nothing new for us. So we have been doing it, we have been operationalizing it in the real world. Every bank in the US has somebody like me, chief model risk officer, who the head will roll first if we have any problem with our models. So it's very high occupational hazard, the job that I have. In the beginning of SR 11.7, when someone have tenure more than 3 years at my position, we congratulate each other because it's very hazardous job at that time. Now it's a lot more stable because we've been practicing this and people know how to do this. Let's switch a little bit more specific on the risk and machine learning in particular and what we worry about and the problem that we do and some kind of, I'm going to take a swipe a little bit in the how people typically practice machine learning. So the risk not only when we build model and deploy model. Risks are changing in machine learning. In real world, many of you know this, that shit happen when you put model in production, right? You have environment change, market change, data change. When you put model that is the best, you put it, shit always happen, all right? So those kind of things that we worry about, and compounded by retraining in machine learning. Because retraining and machine learning is changing model. Your model that used to be okay, not racist, can be racist. Your model that's not discriminatory between male and female can be discriminatory if you retrain it. So retraining also need to be very careful, just like in the model development. So I'll share with you a few things that we care about. In general, when we're thinking about model validation, we're thinking about, are we going to put this model in production? So in regulated industry, like banking and US Bank, every 3 model developer, we have 1 model validator, independent, report to different group, completely report to different group. For every 3 model developer, 1 model validator. So in Wells Fargo, we have about 1,400 people across the company, our data scientists, 1,400 data scientists. A third of them is in model validation. And we have one of those here. There's Arjun is one of the head of model validation. So for every 3 model developer, 1 model validation. We have about 1,400, like I said, 1,000 of them in India, in the US, about 400 of them in India. Right, Arjun? Yeah? So we have a big data science group here in India serving the entire enterprise, the entire company in Wells Fargo. So one of the two things that we talk about, and this is what in the SR 11.7 as well. One is we care about conceptual soundness. We have to, when you build model, the model has to be conceptually sound. The model validation will be tested. And now let me come back a little bit. The role between model developer and model validator. What do model validator do? Model validator is not a quality assurance function. It's not. Okay? So in the I'm making equivalent analogy with the software development side. Model developer is like software engineer, software developer. Model validator are not QA function. They're not equivalent to quality assurance. That's the responsibility of model development activity to do quality assurance. Model validator equivalent to computer hacker. They're going to hack the model. They're going to show how the model will fail. They're going to exploit, they're going to find model weakness, and they're going to exploit it. That's the goal and that's the focus of model validation. They hack model, they show the model will be wrong. And they will find a way to find that model will be bad. And then identifying how bad that will be and how much harm to the company, how much harm to the customer. So here are the things that model validator are doing. 1, on the conceptual soundness. 2, they do outcome testing. In the conceptual soundness, let me talk about a few things. First and foremost, explainability, interpretability. We're going to talk about that a little bit more in a little bit more detail. It's very, very critical. And the problem in explainability, interpretability, particularly in high-risk application, we deal today with a lot of buzzword that is so-called XAI, explainable AI, the snake oil of AI. We have a black box model. We're going to try to explain it. We try to explain something that's unexplainable by applying fancy math, so-called sharp, lime, and all of those alphabet soup of snake oil AI. Try to explain something. Those two, probably okay, probably useful to get rough idea. But those tools can be easily wrong and inconsistent. So in very, very high-risk application in banking, we are not allowing people to use those kind of tools. The model has to be inherently interpretable. And when we talk about inherently interpretable, it's not the old tool in statistics. It's not regression. It's not decision tree. We're talking about ensemble model, how to make gradient boosting machine, how design deep learning to be inherently interpretable. So we're talking about sophisticated machine learning tool, but you architect it in a way that will be inherently interpretable, so we don't need to use all those fake explainers. That's for high-risk application. To do that, require more scale. We cannot just apply those sharp, lime, and all of those things. For low-risk application in banking, we allow to do that. Use very rough tool, like sharp and lime, that's okay. But for high-risk application, we're going to talk about that a little bit more. The other thing that we talk about is overfitting and causality, and that will relate on the outcome analysis. Let me give you something on this. Every machine learning model overfit, every one of them. We just don't detect it. Why? Because machine learning model is built under very, very strong assumption that they are IID. The testing data will come from the same distribution of training data. That's why the practice is we split the training and testing data. I built it using training data. I'm doing it, test it with testing data. And I'm running all kind of auto ML, get the leaderboard, every vendor doing this. Get in scikit-learn 2, you get the best model you pick. Right? That's the practice today. Real world, remember my previous chart? Remember the previous chart say, real world, shift happen. Data shift, training and testing, model use, exposed to completely different things. So when at the overfit in the regime of like machine learning, overly parameterized model, you will not detect if you split randomly coming from the same distribution. So if I want to build a machine learning with the best performance under testing data, simply build the most complicated model. It will get the best performance. Now I will show you in the next page just an example. So the horizontal is complexity of model. In deep learning, is number of layer, number of neuron. In gradient boosting machine, is depth of tree, number of estimator, how many round of boosting that you do. So when you train the model, you split randomly, you build a model, the more complex model on the training, it will get smaller and smaller, it can go even to 0. On the testing that come from the same distribution, you don't see the overfitting. It gets better and better too, and flat. You don't see it. So when people do, let's run hyperparameter optimization. Why? Just put the most complex. You'll do it. You don't need to run hyperparameter optimization, right? When the data training and testing are from the same distribution. This is a very, very typical in machine learning when we're dealing with the regime of overly parameterized. I say overly parameterized. Let me give you an example. It's very simple things. Gradient boosting machine. I'll do this one. It's the simplest one, gradient boosting machine, because everybody knows 3. Let's say 3 depth 7. When 3 depth 7, I will have 2 to the 7 leaves, 128 leaves. That 3 converting original input into pin into the leaves, which is 1010, doing one-hot encoding. We in machine learning call it one-hot encoding. So if I have 3 depth 7, do one-hot encoding 128. Then you can regress it, the result will be the same as 3. If I boost it 1,000 times, 128 times 1,000, I am doing one-hot encoding, 128,000. So suddenly your variable is 128,000. And then if you do linear regression on that, the result is the same as boosting or even better. If you don't believe it, try it at home, right? After do that, convert into one-hot encoding and then regress it. So we're dealing with model with highly overly parameterized. The interesting things when we're dealing with highly parameterized like that, you will not see overfitting. You will see something like that. The more complex the model is, the better. If the data from the same distribution doesn't change. So when you build machine learning, you build it, you clean the data and all of those things, then you split it, you basically overfitting. You will not detect the overfit. That's called benign overfitting. neural deep learning people have a lot of research on this. It's called double descent. So every machine learning overfit. So what's the problem with overfitting? When the noise changes a little bit, the performance crumbles. That's why when you build model, have AUC of 0.8, you deploy it, it's suddenly 0.6. Right? That's very common. Model becoming super sensitive. That's the problem with robustness in the outcome testing. The model is not robust. In machine vision is probably very problematic on this. I collect data using one camera, I deploy it in various cameras, model doesn't work. So that's the typical thing. The other thing that happens in overfitting is model, when distribution shift, model also perform very bad. So we care a lot about the overfitting issue. We care a lot about causality. The causality in banking is very, very important for many applications. For example, credit scoring. We approve credit. Once we approve credit, the credits stay with us until the next recession. So the model has to be good regardless of the time. We cannot just keep retraining. You have to have model that is risk invariance, because once you approve it, the customer stuck with us. Unlike fintech. Fintech, you approve it, then you sell it to other banks or other hedge funds. Right? It's not my problem anymore. So if you fintech, you don't care about model that is invariance. You care about, can I sell it to anybody that's stupid enough willing to buy this? Right? So bank is very different. We originate loan and we stuck with it. Our model needs to be risk invariance. Because of that, we cannot just simply put any factors. That's good now. This is the irony about model. The irony about all of these things. Model works when we don't need model. Models don't work when we need it. Yeah? In a good time, in a good economic time, nobody needs credit model. Just approve anybody. Everybody will repay their loan in a good time. You don't really need model. In a bad time, you need model. Model doesn't work. Case in point, during COVID-19, when COVID-19 hit, all model went out ORI. So this is the irony of what this thing. So what we care about in model validation is we want to develop model. We want to deploy model that works in any different condition. I used to, early in my career, I was an engineer. When I left, I was one of the design manager for Ford Motor Company. My team designed V6 and V8 engine for North America. So when I designed my engine to work in high altitude Colorado, where barometric pressure is low. My engine also has to work in the Death Valley, California, where temperature is 140 degrees Fahrenheit. My engine has to work equally well in Miami in hot, humid temperature. And also have to perform well in Bemidji, Minnesota, where the temperature is minus 40 degrees. So when we build model for banks, we need to do this. Particularly for things that require risk invariance. We cannot just, let's retrain it every 15 minutes. Let's retrain it every month. Let's retrain it, some application do. Dealing with fraud, you probably retrain it more frequently because scenario change. But in a lot of applications that we do, the model has to be risk invariance. So I want to make sure that retraining, frequent retraining, is not an excuse of poor conceptually sound design because it's overfit and causality are not being thought. It's not being designed. So a lot of things happening on the retraining because they just keep fitting noise. That's why you need to retrain. Okay. So in the outcome analysis, we worry about a few things. We worry about weak spot, where the model will be wrong, where the model will be weak. And this is a problem with the community in machine learning. We have complicated machinery, and then we make decision which model we pick based on single measure. AUC, F1 score, MSE, single number to decide which model. All AutoML leaderboard is doing that. Heck, Kaggle competition encourages that. You win 1 point, 2 decimal digit, you win the competition. The model that is the best in that, it can be model that's the worst. Because when things shift, you shift to a region that's really bad. Or have the model not robust. With a small perturbation, the model performs worse. So this culture, the Kaggle culture of judging model, Kaggle culture of choosing model and developing model, in real world, create disaster. Create a situation where when model is real, we really need model don't work. So that's what we need to talk about. So I'm making a plea. Well, whoever run a competition, please don't run that kind of competition. Run competition that's more real. So this is, I'm using the analogy in the martial art world. So we have the martial artist, the grandmaster of martial art, that very expert on this, but never really fight. That's the people like Andrew Ng and company, right? The grandmaster. Never really fight. And then we have people that fight in a very well-controlled environment, competition. That's Kaggle competition. It's very good to do this, but it's only practice. And then real world, which is street fighting. Everything goes. You try to use what you do in martial art competition, in street fighting, you will be killed. That's what we're dealing with here in real world. That's what we're dealing with in the high-risk environment that we do. So, model robustness, resiliency, and all of those are very, very critical for us. And I talk about bias and fairness as well. Model cannot be discriminatory. So when building model in high-risk application like what we do, we have to think about all of this. Not only AUC, not only MSE. We have to worry about all of these things and then pick model that will be safe and sound when we deploy. All right, I am going to go to one more topic that want to go a little bit more depth, a little bit. Okay? So, but before going to that topic, I want to illustrate the robustness with very, very simple examples. So I'm going to flip quickly on one example. Then I'm going to go to one more topic that we're going to do. Here is an example of robustness. Okay? So I built model. Okay, and this is very simple example. I built model, I have XGBoost model, and I have Deep ReLU network model with early stopping and dropout, right, to regularize it. And then one more Deep ReLU network that I regularize it. I make it smaller using L1 penalty to make it really smaller. Then I look at the performance. So this is prediction. MSE, the smaller the better. So when you look at this, the blue one is the winner. XGBoost model is the winner. That's the one that win Kaggle competition, right? That's the winner. And then what happened? Data is noisy. We inject a little noise on the input, on the testing data. Let's inject a little bit noise. 1% standard deviation. Okay, 0.001. 1% standard deviation. Inject noise on the input. And let's look at the output. What happened? What happened with the best model? The performance. Degrade the fastest. Right? And if the noise getting bigger, the model is really terrible. Look at that. You see the MSE going up very rapidly in real world. The other model, the simplest model, the green one, that lost the worst in the leaderboard. What happened in real world? Performed the best. So, did we do this? Have you done it when you build model and test model? This is a very basic, simple stuff. Okay, I just do this illustration. I can go on for other things. But let me go back to the topic that I want to talk about. The topic is about interpretability. Let me go to my slide. All right. So I talk about AutoML. It can be many models. Perform almost the same. More complex model, they perform almost the same. Which one to pick? You pick with minute winner in the leaderboard, you pick one. But really, we have a lot of models. Every point in there is a model. So we have a lot of model alternatives. Many models. Performance almost the same. Yeah? But yet they are very different models. Some of them more robust than the other, some of them more discriminatory than the other. So in machine learning, we have this multiplicity. We have a lot of alternatives. Their performance almost the same, but they are very different models. And some of them, by the way, have very good performance. The model doesn't make sense. If we look at the impact between input and output, relationship between an output, the relationship doesn't make sense. Models that don't make sense can still have very good performance. That's what machine learning problem. So judging model based on outcome alone is not enough. We need to understand the relationship between input and output. Those people inventing XAI. But XAI tool, like I said, all those post-hoc explainability tool that try to explain model, they are not exact. They can be wrong. So for critical application, we need model that's inherently interpretable. That's what I'm going to talk about. Okay? So when we talk about explainable machine learning, we have two streams. The stream at the top, model that intrinsically interpretable. And then the stream at the bottom, the application of what I call it snake oil AI, XAI. Okay? Apply post-hoc explainability. I'm not going to talk about the one at the bottom because that's problematic. I'm going to talk specifically on that. Let's talk about deep learning in this example. Deep learning, we think, is a model that the most black box, right? The most difficult to explain. Well, if we know it and we architect it correctly and we understand, we choose things correctly, it can be the most interpretable model, just like statistical regression model. Let me give a quick example on this. I am putting ReLU network. ReLU is basically using ReLU activation function. If the value is bigger than certain threshold, it's linear. If value is smaller than certain threshold, it's zero. It's basically when the neuron is on, it's linear. So for every sample, we can see which neurons are on and off and trace all the neurons that are on. If you have linear, combined with linear, still linear. Combined with another linear for next layer, still linear. Combined with multiple linear, still linear. So every sample in Deep ReLU network degenerate into linear model. Every sample in Deep ReLU network, regardless of how deep or big, degenerate into linear model. If it's linear model, we have the explanation because just like regression, we have the coefficient. We don't need chat. We don't need lime. We have the regression equation. It's just in the case. So what happened in Deep ReLU network is just basically partition region. in a very, it's partitioning the region. And each region is linear model. That's what it is. No more than that. So you can explain for every decision in ReLU network why the decision is such and such. So that's what this one is. Now, let's see how Lime and Shap, all those post-hoc explainability things that we do. Now, because we know Deep ReLU, we know exactly the explanation, we can compare how truthful, how trustworthy Lime and Shap compared to the reality. The result is not very good. We know the truth. So people and XAI use Lime and Shap with faith. Instead, the field is called data science, but people applying faith instead of that. Okay? So I picked just a few examples on this. I am going to stop right here so that I can talk about this in more detail, but let's do question and answer for the last 5 minutes.